Okay, let's go ahead and get started. Thank all of you guys for taking some time out of today to come and listen to one of the Green Bank Observatory community Zoom talks that we've been having on a bi-weekly basis. Excuse me. I'm Karen O'Neill. I'm the director here at Green Bank Observatory, and I'll kick this off with just a few-minute overview. Before I get started, just a reminder to everybody that if you have any questions, please put them into the Q&A window, and we'll go through all of those at the end of this and give you guys a chance to hear your answers as best we can. So with that, again, I'll give you a little bit of Green Bank Observatory news, and then we'll rapidly move on to the highlight of the day, which is a science presentation by Kat Barger at Texas Christian University on the hydrodynamic instabilities along infalling high velocity cloud complex A. So with that, let me just tell you a little bit about what's going on here in Green Bank. Of course, COVID remains our primary concern. The bad news is the Pocahontas County is reaching a very high infectious rate. It's one of the top within the counties within the state of West Virginia for their number of infections. Were we to have 100,000 people in the county, we would have 183.6 infections just over the last 7 days. We don't quite have that many people, but that's an average put together by the Harvard Health Institute. Here this says schools are remote in the county. Actually, it's across the state of West Virginia, just like across most of the U.S. Schools are, in fact, going back into session. We had a full day of school yesterday, but today we're snowed out, so the kids are all back home again. But the good news in all of this is vaccines are getting distributed. The state of West Virginia is doing a fantastic job at getting those vaccines that they have out into the community. And in fact, within Green Bank Observatory itself, a number of our staff, because of their work through volunteer services with emergency medical services, for example, have already gotten vaccinated and are getting their second doses today. So that's good news and showing a bit of light at the end of the tunnel with all of this. As I've been saying since all of this started 10 months ago, Green Bank telescope remains in full operation 24 hours a day, 7 days a week. Everything seems to be moving along. And although things might be going slower than usual, the site protocols continue to work. We've had no work-related cases of COVID-19. And for the most part, operations continue with the telescope, as well as all of our progress on the various instrument projects that we have going on. Our high frequency season is well underway. As is typical every year, we've had a few weather outages, had some work going on the Argus receiver to improve the calibration system for it. And other good news is the LASSI instrument is being commissioned. This is the laser scanning instrument that's going to provide us with a much better surface across a wider variety of weather conditions that we've been able to have, giving us much higher sensitivities than we've been able to have, particularly, for example, during the summer months, during the daytime. So that instrument seems to be working quite well and is up on the telescope, and will continue to be taking data so we can fully commission it and then eventually get it out to be used by the general observers. Other things going on, big news, of course, is the GBT proposal deadline is coming up on February the 1st. Deadline is at 5 p.m. Eastern Standard Time. That's 2100 UTC, not OTC. As a reminder too, this is a February deadline, so that means large proposals may be submitted this deadline. The next time large proposals can be submitted will be next February. So particularly if you're thinking about large proposals, make sure you get it in this round. And again, this proposal deadline is for the 20B semester. So that's August 1st, 2021 to January 30th, 2022. More details on this, you can just go to the Green Bank Observatory site and then go through science and GBT observers, and you'll find the proposal call there, or you can go to this link that I've listed. The other deadline coming up is our summer research opportunities. This deadline is also February the 1st. You can get to this through our careers site. This is for our REU program that we share with NRAO, as well as our PING program, which is focused on minority students in the STEM. And we also have a number of internships at the undergraduate and graduate level. So all of those applications go through the same system, and you can fill out within that application system the type of program that you're applying for, or all of the types if you want to apply for all of them. So again, just go to our website there and you'll be able to find out more about our summer research opportunities. Just a couple other things going on. The next community Zoom is coming up. It's not highlighting AAS posters. I apologize for that. Next community Zoom is coming up in 2 weeks from now, and we'll continue every 2 weeks through the spring. Our observer training workshop on February 9th and 10th is actually full. There's no room for new folks there. The next one is tentatively scheduled for May 24th to 26th, and the sign up for that should be out very soon. right after the February Observer Training Workshop. So I encourage you, if you're interested in learning how to use a GBT, if you've got science to be done on the GBT or you just want a refresher, I encourage you to sign up for that. And then, of course, our single dish training school is the week of September the 13th, and that registration should be open soon as well. So with that, I would like to thank you guys again for coming and listening to the talk. And I'm now going to hand this off to Kat to talk about the High Velocity Cloud Complex A. So Kat, it's all yours.
Hi, everyone. Let's see. Thank you for inviting me. Okay, there we go. Always a little bit of logistics getting it first started. All right, well, welcome everybody. Today we're here to learn about the gas cycle of our galaxy a bit. When we think about what's happening with our galaxy, it's forming stars, planets, and all those things take up gas. As our galaxy goes along, it's going to use up more and more of its material. And so eventually it'll run out of material altogether. That is, of course, if our galaxy lived in a closed box and wasn't interacting with its environment. And so if our galaxy is able to capture and draw in new gaseous supplies, then we can keep forming stars and solar systems for longer. And so a big question we have is, how much gas is there for our galaxy to capture? And if there's a gas cloud that's flowing into our galaxy, how easily can it actually travel to our galaxy? And what's happening to it along its way? And so today we're talking about High Velocity Cloud Complex A, which is a gas cloud that is on a journey to our galaxy, regular gravitational pull, bringing it in. It contains 2 million times the mass of the sun in gas. And so it can form quite a bit of stars and planets. That is, of course, if it can reach our disk. Okay, so it's being drawn in by the Milky Way. This gas cloud, I should point out, has a very low chemical abundance, which indicates that it's likely not from our own galaxy. It's material that's being drawn in for the first time. And so we're drawing this gas cloud in. And as we do so, we see that this gas cloud's getting very tethered and beaten up and mangled a bit. And there's a bunch of features on it that look like it's not doing so well during its journey. So in order to understand what's happening to it, we use the Green Bank telescope to observe it at over 100,000 locations in using H1 21 centimeter spectroscopy. So that way we could really map out what's happening to this gas cloud as it's traveling through the Milky Way's halo. And so remember that as this gas cloud's traveling through the halo, one of the reasons why we're seeing all these interesting structures over here is because, it has to, one, travel through the halo. And remember, the halo is going to be a very hot, low density gas, 1,000,000 degrees Kelvin. And additionally, it's also interacting with an ionizing radiation field from our galaxy. And so this over here is a cartoon representing what occurs to gas clouds as they flow in towards our galaxy, where the gas clouds, they might start out cool, maybe as signified by these blue and green kind of colors. And then maybe they'll get heated up and ionized. And then maybe even the outer skin of them might get heated and ionized and really banged up. And the inner regions might be able to keep themselves protected. And then additionally, they have to travel through the ionizing radiation field of our own galaxy and background galaxies as well. And so here's the model for the ionizing radiation field of our galaxy, where this is representing the disk of our galaxy. This would be along the poles, and this would be the contribution from the Magellanic clouds. And High Velocity Cloud Complex A is coming in. It's much closer, but it's coming in along over here, kind of above the disk. So as these gas clouds come in above the disk, notice that they get really beat up with ionizing radiation as well. And so that's also a source to disrupt these gas clouds. So what do we see when we look at Complex A? Okay, well, since these are spectroscopically resolved observations, we can look at all more than 100,000 locations, and we can characterize the motions of the gas at different portions of it. And what we did was we did Gaussian decompositions of all over 100,000 spectra. So then that way we could characterize not just the bulk motion, the average motion at every single spot, but to get an idea what even the wispy components are doing and all those other things. And so here's an example of those Gaussian decompositions over here towards the bright core regions of this gas cloud. And these bright core regions are essentially just the locations where the H1 gas is has a higher column density. So this location here, here, and so forth as we go along. This portion of the gas cloud is the portion that's leading the charge to our galaxy. And then over here we have the trailing side that's behind as complex A is journeying towards our galaxy. Okay, so we have 100,000, more than 100,000 sight lines, all spectroscopically resolved. All we've done Gaussian decompositions for it. So that means we can really look to see what's happening with this motion of this gas cloud. And so what I have for you today is I have a two-dimensional map that we're going to rotate into a third dimension. So then that way we can to see how the gas cloud's moving along our line of sight. So first, to orientate yourself, we have the galactic longitude and the latitude over here. This is the portion of the gas cloud that's in front, and this is the trailing part. Our orange colored data points represent higher column density, and the gray and yellow represent lower column density gas. Okay, so now we're gonna rotate this image into our third dimension. And so on our vertical axes, in just a second, we'll have a local standard of rest velocity, where the bottom of that axis is going to be gas that's moving faster towards our galaxy. And at the top over here, we have material that's moving slower towards our galaxy. And take a mental note as far as like which colors you see at which locations at the higher and lower. We're about to rotate into a really nice position. We'll see that there's going to be a lot of orange on the bottom of this plot here. And so look at all this orange over here. So that's the higher column density gas. This gas is moving faster towards our galaxy, leading the charge. And since it's leading the charge, that's the material that is able to protect itself and really push through the halo pretty well, versus the stuff that's up here is the material that's really lagging behind. This is the lower density material. And so this is the material that's essentially falling off of our of the gas cloud. And notice that we have some very, very interesting structures, like this structure right here, where that says that there is like a pretty rapid deceleration of what's happening with the gas right there. And so to orientate ourselves, this is the leading portion of the gas cloud, and this part is the trailing part. And so the part that's leading the charge is lower in the galactic halo, where the halo gas density is going to be thicker. But on top of that, the leading portion of this complex is only a couple kiloparsecs above the galactic plane. Well, that means that there's going to be possibly some extraplanar gas, maybe some warm ionized medium material there that it's maybe even already starting to interact with. And so this fun kind of behavior right here might be because maybe we're already starting to interact with the upper portions of the disk of the Milky Way. Okay, now we'll go ahead and keep rotating along, and we'll get ourselves back to our two-dimensional frame, two-dimensional image on the sky. All right, so to get another view, we're able to map out this gas cloud in column density. Milky Way down here, direction of motion in this particular direction over here. So this is the column density map that you saw just a second ago. But we're also able to, again, look at the motions of the gas cloud. So this is similar to what we saw before, but in color coded. This is color coded, so then that way we can see what the gas cloud is doing in galactic standard of rest. So relative to the motion of our galaxy. And then when we do it relative to the motion of our galaxy, we can see like a nice velocity gradient along it. And so using that, we can make estimates and predictions for like, when is this gas cloud going to reach our galaxy? You know, assuming very simple assumptions about what's happening with the acceleration and so forth. And that'll be on the order of 70 million years from now. And on top of that, with those Gaussian decompositions, we can also get an idea of what's happening with the width of the lines. And so here's a map of the full width half max of the lines at all the locations. And since we're looking at a two-dimensional plot, but there's multiple components fit along each sight line, the colors that are on the top of the figure are the ones with higher column density. So just so you know, you got to choose something. All right. And so just to highlight a couple of the regions, just that way we can see what it's looking like at a couple of different spots. This is the portion of the gas cloud that's in the very front, that high density H1 region that's right in the front of this gas cloud as it's coming towards our galaxy. And over here we have that same kind of representation, two-dimensional in the sky, latitude and longitude, column density right here. And so everything on the top is going to be colored for column density. And then on the bottom here, we have a two-dimensional representation again, latitude, longitude, spatially, but now we're coloring with respect to the width of the line. And on these ones over here, we've changed our axes so that we have longitude, latitude, and over here we have motion, local center of Earth rest. And so this kind of gives us like different snapshots of as we're rotating through that video that we saw earlier, you know, what's going on in the gas cloud as you rotate it in with different perspectives. And so you can see that big, huge U shape that we saw earlier, indicating that gas connecting some of those denser cores right in between some denser cores is really decelerating and getting mangled. And then we can similarly look to see, okay, well, how does that material look when we think about its line width? And so this is the lower column density gas decelerating downwards. And when we look at the line widths of it, you know, this is material that is getting broader and broader. And that makes sense. I mean, there's probably a lot more non-thermal motions, you know, turbulence and things that is occurring in this region over here. And so that's also interesting to see that, you know, we have these, the cooler colors over here, the yellows, and so forth, on the bottom over here, which is the gas that is going to be traveling faster towards our galaxy, that's maintaining its structural integrity. And then as we're going higher in this two-dimensional image, we're getting to deeper and deeper shades of color here to the warmer end of this color scale, the broader and broader lines, so that the gas is either getting much warmer as it's getting lower column density, or it's getting much more turbulent, probably a combination thereof, you know. Oh, I'm going to show you one more. This is the region, the back end of the gas cloud. This is the very, very trailing side of it. And it's a portion of the gas cloud that's kind of hanging off as a Rayleigh-Taylor instability. I'll show you that again later on, but we have these fun instabilities that we observe all over this gas cloud. And so on the back side, here's the converse of what we see, where we also have the same two-dimensional image in column density, full width half max. And then over here, we can then look at it with velocity on our y-axis. And so now this is going to be the side that's going faster here, and then the slower moving gas over here. I don't see as much crazy structure in this one, but we do see a similar trend where the widths the broader lines are again on the top end of the plot. So it's just kind of fun to see at different perspectives. And so since there's so much data here, it's a lot to comb through it and to interpret it, to figure out what's going on. And so one way that can be very useful is to just do some basic histograms of what's happening at different regions. And so if we look at each of those core regions, where those core regions again are those locations where you have dense H1, and you just look at the full width half max and you do simple histograms to just say, okay, well, what is happening in that particular region and how is it changing? And that's essentially all we did. And then what we have here, there's some nice markers here, vertical markers, that just indicate what these full width half mass would correspond to if you only assumed that the gas was being non-thermal broadened. And so, you would expect it to be about 10,000 degrees Kelvin, right around here at full width half max of 21 kilometers a second. And we can go through and we can look at each of the different cores, and it bounces around a lot. The leading core was a lot more kind of all over the place. So the leading core is A0. And then as we increase our core number to, core 1, A1, 2, 3, 4, and all those, you're getting farther and farther along the complex A to the backside of it. Okay, so even that is kind of a lot to disentangle. It's like, okay, well, what is the big trend that we're seeing? Well, when we plot up the median line widths for all those, so just the median widths for every single location, this is essentially what we have for the leading portion over it. So this is angular offset from the leading core. So this is right at the front of the gas cloud. And then this is what you would have for towards the backside of the gas cloud. And now these uncertainties are extraordinarily large because, this is just looking at simple medians, but it can at least give us a general trend. And if we fit a line and look at an uncertainty envelope, this is kind of like the trend that we would get for all of those. We have the median full width half max over here. And if you like line widths instead of full width half max, that would be what that corresponds to. Here are the cores, so you can tell which core we're looking at. And then this would be the only thermal broadening temperature that it would correspond to. And so there's a very slight kind of gradual trend that it's raising more and more. And so those would correspond to a bit of a difference of around 4,000 Kelvin warmer on the backside if it was only non-thermal broadening, only thermal broadening, or if there was non-thermal broadening, it would result in an increase of broadening by about 14 kilometers a second. And so probably a bit of being heated up and probably a bit more turbulent. It is the backside of a gas cloud that's dissolving into a halo after all. Okay. So let's go ahead and look at this. And so when we look at this gas cloud and we think about what's happening over it, remember that we have big chunks of it that are slowing down quite rapidly, parts of it that are moving much faster. And so, it's there's a lot more hiding in here for us to understand as far as how the turbulence and broadening and heating are going. But I think that this at least gives us like a good starting point. I want to highlight some interesting structures that we see in this particular gas cloud, just morphological signatures along the entire length of this gas cloud. It's becoming elongated, it's becoming fractured. There's parts of it that are kind of oozing off the main body. We have the Milky Way's gravitational pull going in this particular direction over here. This is a gas cloud that has a higher density than the surrounding halo medium. And so what's happening is that you get buoyancy instabilities where the high density gas essentially falls through the halo medium below it. And so this gas cloud is essentially dripping through the halo gas is what's happening here. And then as it's dripping through, since it's traveling through the halo, well, that material will get pushed backwards in the direction of motion through just apparent wind processes. So, you know, that's like the same kind of process for like let's say you're on your bicycle and there's no wind outside and you're not pedaling. Well, there's no wind. Well, as soon as you start pedaling very rapidly, you feel a wind on your face. And so as this gas cloud is traveling through the halo, it's also feeling an apparent wind that's pushing it backwards. On the top side of this gas cloud, we also have weird vertical structures protruding tangentially off the surface of this gas cloud. And those are likely Kelvin-Helmholtz instabilities, which are processes in which when the gas cloud travels through the halo, it's rubbing against the halo. And as it rubs against the halo, you form these shear instabilities where the halo will push the cloud inwards. And as the cloud gets pushed inwards, the skin will push in. And when the skin pushes in, it runs into the inner portions of itself, and the inner portions of itself push back. And then the halo pushes back and forth and back and forth. And you can amplify those structures, and eventually you can get these interesting protruding structures that come tangentially off the surface of the gas cloud. And so overall, we find that as complex A is traveling through the halo, it is becoming elongated, fractured. Portions of it are protruding out more and more into the halo. It's slowing down. Overall, the more and more its surface area increases, the more rapidly it's going to dissolve into the halo. And so this gas cloud is getting mangled, and not all of it's going to survive the journey to our galaxy. And so, you know, this gives us great insight on how these instabilities work and how these gas clouds are affected, and why so much of this material evaporates into the halo so rapidly. This gas cloud has 2 million solar masses of material, but you know, maybe only half or a quarter of it or less will actually reach it. And so we'll have less future stars forming in our galaxy, but you know, now we can understand that cycle better. Thank you.
Thank you, Kath, for an absolutely fantastic talk. That was wonderful. If anybody has any questions, please, like I said, put them into the Q&A. I see we already have a few showing up. So Kat, I'll just read those out to you so you can then focus on your talk and we can go from there. So the first question is, this seems like a huge area to map. How much telescope time did this take?
Oh, yeah. Okay. So we'll bring up, here's the map over here. And so we have like, what is this? It's more than 30 degrees in longitude, and then another 20 degrees in latitude, you know, plus a little bit more. But of course, the corners you don't have to map out as much. You only care about the region on the gas cloud. We got, I think our proposal, we first got 70 hours to map this backside. And then I think we were awarded another maybe 15 hours. There was a big government shutdown, and then things got all messed up and they needed some filler time. So we got a little bit more time to really map out this backside. And so that was about 85 hours in total for this region. And now the leading side, the leading 2/3 of it, we were fortunate enough to extract from the GBT archive. And so it was relatively cheap for how large this gas cloud is, just because we were able to piggyback off of the existing observations.
Thank you. I'm going to combine two questions here together. So what is the total H1 mass of the gas cloud? And highly related, how did you determine the distance to the gas cloud?
Oh yeah, okay, so the H1 mass is roughly about 1 million solar masses, and the ionized mass is roughly the same. And we got the ionized mass from our 2012 study, where we mapped this entire thing out in H alpha using the Wisconsin H alpha mapper telescope. To get the distance of this particular gas cloud, the that was some work that I did, plus some work that other people have done as well. One of the best ways to get distances to these gas clouds, the best way really, is to anchor them using stars at known distances using absorption line spectroscopy. And what you do is if you have a star that lies at a known distance, when you look at it, look at that star, you look for absorption features associated with the gas cloud. If you see absorption features in that stellar spectrum, then you know that the cloud lies in front of the star. If you don't, then the star lies in front of the cloud. And so it's more of like a anchoring, bracketing kind of game. And so this gas cloud has been bracketed at 3 locations from this technique. And then the indirect method that I did in the 2012 study using the H-alpha observations, what we did was, since H-alpha mission traces ionized gas, we just said, okay, well, if we have this much ionized gas, what the heck is ionizing it? If we say it's only photoionization, which actually seemed to match out pretty well with what was happening with some multi-line stuff, then how close can we slide this gas cloud to our galaxy before we get too much ionization, not enough? You know, where is that Goldilocks just right for how much ionization we see in that gas cloud? And then that enabled us to place tighter predictions on the distance of this gas cloud that matched the stars studies really well.
Okay, next question. Would it make sense to try to confirm the temperature structure by looking for ionization tracers and abundances through the optical spectroscopy towards background galaxies in the region?
Probably. The bit of temperature stuff that I did in the 2012 study using H-alpha, it was a 1 degree on the sky per beam, and we were able to get that the temperature of this gas for the warm part, the warm phase, was roughly about 10,000 degrees Kelvin. But that resolution is so cruddy in comparison to like what GBT is offering here. And I don't know how many background quasars or AGN could be available to do that. I think I should probably look, you know, the HST cycle, next proposal cycle is coming up, so that could be a good idea.
Another question, are there other similar clouds that would be worth mapping? And if so, what sort of improvement to survey speed would be needed to make it feasible?
Oh, okay. So one other gas cloud has been mapped out equally well. This particular gas cloud is the best mapped gas cloud for one that is coming towards our galaxy for the first time. But the Smith cloud is one that's in a galactic fountain process. And so Jay Lockman has led those efforts. And it's very fun to see like the differences in structures, because these are both gas clouds that are in very advanced stages of accreting onto our galaxy. Now, I'm not really sure what advances we would need to do to increase our ability to map this out. I mean, the GBT is a fantastic instrument, but you know, I ask for time and just like, how much time do I need? Okay, let's get it done. So I'll let the GBT crew tell us like what advances we need on that side.
Well, cameras are always great, but I'm going to keep going on your questions because you have quite a few still here. How is the metallicity determined for the complex?
Yeah, at the locations where there was stellar absorption, you know, towards the background stars, or where they were doing the distance measurements, they were able to constrain the metallicity of a few elements there. And then in that 2012 study I did, we had H-alpha, sulfur 2, and nitrogen 2 observations, and we did some photoionization or radiative transfer simulations too. And all together, all those studies together place the metallicity of this gas cloud to be roughly about 1/10 solar. And the reason why I'm very much thinking that it's not coming from our galaxy, because again, 1/10 solar, so that's probably not where it's coming from. But on top of that, that material is probably also not coming from a satellite galaxy, because we look for satellite galaxies in the region and we don't see any. And so likely this is intergalactic medium filament material, since it's also too high metallicity to be a halo gas condensation as well.
All right. Do you find any star formation associated with the cloud?
We don't. This particular gas cloud is too low density to really support star formation. And so like the density of this gas cloud in H1 is probably on the order of of 0.1 times, 0.1 particles per cubic centimeter, so it's pretty low.
All right, last two questions so we can let everybody go. Next one is, do your observations help elucidate the origin of the high velocity cloud complex A?
Yeah, or at the moment, they don't yet, but that doesn't necessarily mean that they can't. And so one of the things that we want to do as a follow-up study is, since we have this rich information, we would like to track the orbit or the motion or the path of this gas cloud better through the halo. And of course, we can get some idea of what's happening along it, but it'd be really good to take account for like the changes in acceleration as it's traveling through from slowing down from ram pressure stripping or speeding up as it's coming closer to the disk and so forth. So doing some tracing back motion analysis path analysis would be good.
And last question, how does your survey properties compare to that of H14PI?
Yeah, the sensitivity of the 4 pi survey, so the all sky survey, that it is, I'm not sure what the sensitivity is off the top of my head. I think it's around 18.3 in log. I know that's how, sorry. So in column density, H1 column density, I think the sensitivity is in log 18.3 for the column density. And then we have a typical sensitivity of 17.9. Some locations better, some locations a little bit worse, depending on, because it's a bit of an archive putting things together. So the sensitivity is much better here. And then I don't remember what the beam size is, but there's a difference in beam size too. And I think we're on the better end of that, but I'd want to double check before I say that, because that is a very good survey as well.
Well, with that, I'm going to thank Kat again for a fantastic talk. Thank everybody for listening, and remind you that our next community Zoom will be February the 3rd. So thank you again, Kat. Bye-bye, everybody.